Hi, my name is Josh Gregory and I would like to present my demonstration project for MAE 535. In this project I decided to demonstrate applied electromagnetics and specifically how a solenoid could be used in an application. The inspiration for this design was to come up with alternatives for a firing mechanism of an airsoft pellet shooting robot that was designed for another class. It is a spring-loaded piston and cylinder mechanism that is driven by a DC motor. This is the design that I've come up with. It basically uses the same principle to fire the pellets, and that is a spring-loaded piston and cylinder. I actually pulled the spring, piston, and cylinder from another gearbox so I could be sure that they would operate the same, and I only had to worry about compressing the spring to drive the firing. The way that we are doing that is with a solenoid, and when the solenoid has applied voltage and current, it will pull in the ferromagnetic rod, which will load the spring. I found that if I took apart a pencil that I had laying around, I could get this plastic sheath that was pretty thin and yet rigid enough to support coils. And also the inner diameter of the sheathing was about 3/16 of an inch, and I could get an off-the-shelf rod. To this I found a caster wheel that I pulled the wheels off of, drilled a hole in, and then welded those to create a spool using JB weld. And then I wrapped 1800 turns of 28 gauge magnet wire around the spool. So I guess here we go, and then we'll fire another. And one more for good measure. You can probably already tell that the pellets are not traveling at the kind of velocity that we would want to see out of this. And so this really begged the question of how to design the solenoid for a known force output, which is where we'll go to now. For this design, I was interested in determining the force acting on the plunger that is applied by the magnetic field of the solenoid. As it turns out, that force is related to the magnitude of the magnetic flux field in the air gap of the solenoid, which actually changes as the plunger travels further into the solenoid. With a few assumptions in the derivation shown on this slide, you can arrive at the equations shown here for force and magnetic flux. After studying the governing equations for this design, I was able to develop two main takeaways from the project. The first is that the diameter of the plunger was actually limiting the maximum force out of the solenoid. Since the B field is expected to saturate around 1 Tesla, that means that no matter how many amp turns the solenoid had, it would be limited to only applying 7.2 Newton force on the plunger that I had chosen. I think this best explains why I was unable to get the compression that I was seeking out of the original spring, regardless of the amount of current that I pushed through the solenoid. Additionally, as you can see in the figure, since the applied force has an inverse square relationship to distance, the linear spring needs to be carefully designed not only at max compression but along the entire path. The second takeaway from my analysis was that the B field is obviously very dependent on the actual construction of the solenoid. I created two finite elements models in FEMM for both the expected dimensions of my solenoid as well as the actual dimensions. Because of extra space in the coil winding, even though I took great care to minimize that, the current density in the space of the solenoid was reduced so much that the flux was actually a tenth of what I expected for the design. The experience and lessons that I learned from this project, I believe, have given me valuable insight into the design process of an electromagnet. I certainly am better equipped to approach this problem again, and I hope that I was able to effectively convey what I learned in this short presentation so that you may also benefit from the lesson. Thank you for tuning into my presentation, and good luck in your designs.